Let's continue our discussion of electric circuits, and we're going to start by taking a look at the autonomous law, Kirchhoff's crazy ski resort, Kirchhoff's law. And Kirchhoff's law deals with the situation of a circuit with multiple circuit elements in parallel and series. It's not just in a straight line. So you can take a look at the example on the screen where we have these batteries in parallel, we have these resistors in parallel or series. What happens if a circuit gets more complicated? And this is where Kirchhoff's rules come into play. To understand Kirchhoff's rules, and there are two of them, there are two fundamental ideas, and I'm going to use a ski resort as the basis for understanding them. If you have a location in your ski resort where skiers can go to the left or go to the right, or maybe they come from the left and the right and then follow a single path towards, say, the ski lift or something, you have as many skiers going into that intersection as you do coming out of it. As many skiers per second entering that junction as leaving that junction. So the first law is going to be based on that. The number of skiers per second going into a location is equal to the number of skiers per second coming out of that location, even if they go off in different directions. The second rule of Kirchhoff, imagine you own the ski resort and you have a snowmobile and you can go around that ski resort, you can go uphill, you can go downhill, it's all the same to you. So you get on your ski resort and you decide to make a trip around it to inspect the place. If you start and if you end in the same location, at the end of all of those paths and all of those ins and outs and lefts and rights you've taken, at the very end your change in altitude is zero. You began and ended in the same place, so the change in altitude is zero. In electric currents and circuits, what do these two rules mean? The first one, the skiers in equals per second in equals the skiers per second out, is basically the current going into a junction equals the current coming out of the junction. The charges per second going in equals the charges per second coming out. And the second one is if you follow a closed path, if you begin and end in the same location and you look at how the voltages change as you go through the different circuit elements, all of those voltage changes add up to zero if you begin and end in the same place. In the figure on the screen in the lower left, some directions for currents have been drawn. There are three possible currents in this, I1, I2, and I3, through the different circuit elements. And if you examine a single junction, for instance, the top junction where the black circle is, you would see that currents I1 and I3 are pointing into it, and current I2 is coming out of it. And so the first rule means that I1 plus I3 must be equal to I2. Now, you might ask, how do I know the direction of the currents? And there's a very simple answer. I just guessed. That's all. I just guessed what the direction of the currents were. And it's okay. It's okay to get this guess wrong because nothing whatsoever bad happens. It's just a matter of a very easy interpretation at the end of all things. So you can put the directions down as anything. It does not matter. You can have it go with a clockwise orientation, a counterclockwise orientation, up, down, does not matter. But once you pick that direction, you have to stick with it. As for going around in a closed loop, when you go through a resistor, now if you're a current going through a resistor, it's like a skier going downhill. The skier going downhill loses voltage, but the skier going downhill loses altitude, and the current going through the resistor loses voltage. But you are not going to be a skier. You are on your snowmobile. So you might just choose to drive that snowmobile up the slope. That's okay. You will be gaining altitude, and we'll see how that translates into a circuit analysis where you can gain voltage as you go through a resistor. We're only going to look at situations no more complicated than what you see on the screen, where it's kind of like a weird figure eight or a symbol for infinity, something like that. And in order to use Kirchhoff's second rule, the so-called loop rule, you need to pick two closed paths. You need to pick two loops. And two of the loops are basically the left side and the right side. But technically there's a third loop that's around the perimeter. But frankly, I only do the first two. It doesn't matter which of the two of the three you pick, but just for the sake of consistency, I look at the first loop and I look at the second loop. Third loop, don't worry about it. But it is there if you want to worry about it. Now, let's take a look at the example on the screen, and we see a mixture of batteries and resistors. And in the first step, I need to guess the directions of the currents. And as I said, it does not matter if I get it wrong. You'll see three currents, and you see I1, I2, and I3 in the figure below. Now, be careful about how you pick your currents. They're always, in this class at least, they're always going to follow this pattern right here. The current through the, on the left-hand side through the 9-volt battery and the current through the 7.31 ohm resistor have to be the same because they're in series with each other. The current through the 4.55 ohm resistor and the 12-volt battery has to be the same. The current through the 8.83 ohm resistor and the current through the 6 ohm resistor has to be the same. But wherever there's a junction, the current can branch into two different directions. And so if I have current going through the 8.83 ohm resistor and it reaches a junction, some of it goes through the 7.31, some of it goes through the 4.55. So all I can say is that the current through the 6 volt and the 8.3 ohm is the same. The current through the battery and the resistor on the left is the same. The current through the battery and the resistor on the right is the same, and that's it. Now, if you look carefully at the directions of the currents I've guessed, if you pick, say, the upper junction, you'll see that I1 is going into it. You'll see that I2 is going into it. You'll see that I3 is going into it. Can that be? Oh, my God. Oh, no. What's going to happen? No, don't worry about it. But once you pick that direction, stick with it. That's the only trick. You stick with it. So we have I1 going into it, I2 going into it, I3 going into it. We have nothing coming out in our drawing. So current going in is I1 plus I2 plus I3. Current coming out is 0. Now that's the node equation or the junction equation, as you wish to call it. We're going to move on to applying the loop rule, and remember we have to pick the two loops. Being unoriginal, I am going to start with the left loop, the one that I had labeled number 1 in the previous diagram, and I'm going to start in the upper left corner, and I'm going to make my closed path go around clockwise. No strong reason, just because. I like doing these things with some consistency, so I don't have to guess, wait, did I build up this equation clockwise or did I build it up counterclockwise? We'll see what I mean by that when I say clockwise versus counterclockwise. Let's just take a look at that first equation. Let's go back to the circuit. And I'm going to start in the very upper left corner, and I'm going to start going clockwise. And the first thing I encounter is the 7.31 ohm resistor. And the current through the 7.31 ohm resistor is I1. And as I continue my clockwise path, I'm going to go through the 8.83 ohm resistor, and the current through that resistor is I2. I then reach the 6-volt battery. I reach the lower junction. If I'm going clockwise, I now start moving to the left, And I keep going, the wire does nothing, 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 nothing. Oh wait, there's a battery, a 9-volt battery. I have to go through that. And then I'm back to where I started. When you go through a resistor, there are two things you have to worry about. You have to worry about which one of the currents is going through that resistor. So for instance, through the 7.31 ohm resistor, the current is I1. Through the 8.83 ohm resistor, the current is I2. And you need to worry about in which direction you are traveling as you go through the resistor. And direction relative to the current through the resistor. If you compare the upper figure with the lower figure on this slide, you will see that if I start in the upper left and I move towards the 7.31 ohm resistor, I am moving with the current I1. And then I take that right turn and I head towards the 8.83 ohm resistor, but there I'm moving against I2. If you are moving with the current, it's like you're on your snowmobile going downhill. And if you're moving against the current, it's like you're on your snowmobile going uphill. So with the resistors, the two questions, what's the current and are you traveling with the current? Those are the two questions you have to ask. There's only one question you have to ask if you encounter a battery. And that question is, in which direction are you going through the battery? Are you going from the long bar to the short bar, or are you going from the short bar to the long bar? If you remember our previous discussion of a battery as a ski lift, the short bar represents the bottom of the ski lift and the long bar represents the top of the ski lift. So after passing through the 8.83 ohm resistor, I now encounter the 6-volt battery, but as I pass through the battery, I'm going from the long bar to the short bar, which means I'm going downhill or down voltage. I am losing 6 volts. I keep going around and around, and as I head back towards where I began, I reach the 9-volt battery, but there I'm going from the short bar to the long bar. I'm going up, so that will be plus 9 volts. Let's take a look at what all of this means in the equation. So, like I said, the first thing we encounter is the 7.31 ohm resistor. The current through it is I1. We are going in the same direction as the current. We are going down voltage. And according to Ohm's law, the voltage difference that we encounter is current times resistance. So the magnitude of the voltage difference is 7.31 ohms times the current I1, and then as we said, we are losing voltage, so the voltage difference is negative 7.31 I1. Next, we encounter the 8.83 ohm resistor. The current through it is I2. We are going against the current. We are going uphill. The potential difference across it, again, Ohm's law applies. The current is I2. The resistance is 8.83. And because we are going uphill or up voltage, the voltage difference that we worry about is positive 8.83 I2. Next, we encounter the 6-volt battery, and we happen to be going from the long bar to the short bar, so we are losing voltage. Notice that I very subtly put the expression that how you determine whether it's positive 6 volts or negative 6 volts is independent of the direction of the current through it. When it comes to a battery, there's only that one question: is it short bar to long bar or long bar to short bar? With the resistors that you have the two questions. Is it which current is it, and in which direction relative to the current are you moving? But with the battery, just the one question. And for this 6-volt battery, we happen to be going down voltage from the long bar to the short bar, negative 6 volts. And then we're left with the 9-volt battery, and as I said before, going from the short bar to the long bar means that we are going up. So that would be positive 9 volts. And all of these potential differences add together, and since this completes the loop, we begin and we end at the same point, all of these differences have to add together to be 0. And we have our first equation from the loop rule. For the second equation, and I encourage you to pause this video and go back to the circuit and predict for yourself what the second equation would be. I'm obviously going to spew it out right here, but pause the video, go back, and make the prediction for what this equation will be. I hope you pause. Let's discuss this second equation. And because I'm unoriginal, I'm going to start in the upper left corner of the second loop, and I'm going to go clockwise. It just helps keep the bookkeeping less painful. And as we go clockwise, starting in the upper left of the loop on the right, we first encounter the 4.55 ohm resistor. We are going against the current, so we are going up voltage, and so Ohm's law says 4.55 times I3, and the fact that we are going against the current means positive 4.55 I3. We then encounter the voltage source. We are going down. We are passing through it from the long bar to the short bar, so negative 12 volts. We then encounter the 6-volt source, and we are going up. We are going from the short bar to the long bar, so that's plus 6. And then finally, the 8.83 ohm resistor, we are going with the current, so minus 8.83 I2. And then we're back to where we started. So all of those differences have to add up to 0. We now have three equations. We have that junction equation, I1 plus I2 plus I3 equals 0. We have the loop equation from the previous slide, and we have the loop equation, the second loop equation on this slide. Three equations, three unknowns, and it's algebra at this point in time. This might be something you'd want to practice on your own. And you hopefully will get the same thing I did. I1 equals negative 0.060 amps, I2 equals negative 0.428 amps, and I3 equals positive 0.488 amps. And this is where you determine whether or not your original guesses for the directions of the currents way back at the beginning of your analysis, which ones were correct. I got a negative value for I1, I got a negative value for I2. Oops, I guessed those directions wrong. I1 is positive 0.060 amps and I2 is positive 0.428 amps, but they're in the opposite direction of what I had guessed back on this slide right here. I guessed those two, they're the wrong direction. Oh no. Life is horrible. Our analysis is totally messed up. No, of course not. You just guessed wrong. Big whoop. You know what the magnitude of the current is, and now you know officially what the direction is. That's all it is. Here's a conceptual question for you. You can see the circuit, and there's a switch, as you can see it, and the switch starts off open. The two voltage sources are identical and ideal. The two bulbs A and B are also identical and ideal. They act as resistors. And we have in the first situation with the switch is open as depicted in the figure, and we basically have a single loop. A 12-volt battery and another 12-volt battery passes through a bulb and passes through a bulb. And so those bulbs are going to be lit up. What would happen, relatively speaking, if we put that switch closed? Do you think the brightnesses of both bulbs would increase? Do you think both would decrease? Do you think one would increase and the other decrease? Or do you think there would be no change at all? Think about it. Let me know if you have a question. So we've discussed resistors. We've discussed resistors in series. We've discussed resistors in parallel. Another common circuit element is the capacitor. And we know what the capacitor is. We can just think of them as parallel plate capacitors. That's good enough for our discussion. What would happen if we had multiple capacitors in a circuit? And again, we're going to compare having them in parallel versus having them in series. And what we get is perhaps a slightly confusing change. Take a look at the circuit on the screen. We have the voltage source on the far left, and it's hooked up to 4 different capacitors labeled unimaginably C1, C2, C3, C4. And the idea of parallels having the same voltage still applies. That idea of parallels having the same voltage is a conservation of energy thing. Conservation of energy applies in way more than just electric circuits, but it does apply in electric circuits. So the voltage difference across C1 and C2 and C3 and C4 all must be equal to the voltage supplied by the battery. And it turns out that the 4 capacitors that you see there in parallel can be combined into one equivalent capacitance. And when they're in parallel, when the capacitors are in parallel, you just add the capacitances together. It's like having one big parallel plate capacitor. You can also use that information to determine the charge on each capacitor. The charge on each capacitor would be equal to, it's based on Q equals CV, capacitance times voltage. So the charge on capacitor 1 is C1 times the voltage. The charge on capacitor 2 is C2 times the voltage, so on and so forth. Capacitors in parallel are just like resistors in series. You just add them up. What about capacitors in series? Capacitors in series are a bit more annoying. Now, I know you see, and I hope you see, that what we have are several different capacitors in series, but notice that there is no wire connecting a portion of this circuit to the actual battery. So on this little kind of H-shaped element right here, the total charge has to be 0. Now, I can get charges building up on the left side and on the right side, and I can get a bunch of negative charges on the left and a bunch of positive charges on the right, but those charges have to be the same in magnitude. And ditto with the middle H, and ditto with the H on the right. And what we get is that the charge across each capacitor, the magnitude of the charge on each plate of each capacitor, has to be the same. When capacitors are in series, just like when resistors are in series, the voltages across the capacitors have to add up to the voltage supplied by the battery. If we look at it in terms of the charge, now all of these capacitors are going to have the same charge. We have Q equals CV. I know what C is. I'm given each of these capacitances, C1, C2, C3, and C4. Q is the same across each. Q equals C1 times the voltage across C1. Q2 is equal to, Q2 is still Q, is equal to C2 times the voltage across C2. The charge across capacitor 3 is still just Q, it's the same as on the others, and it's equal to C3 times the voltage across capacitor 3, and so on and so forth. So we have that equality. The charge across each is the same, so Q is going to be equal to C1 V1 equals C2 V2 equals C3 V3 equals C3 V4. We also have V1 plus V2 plus V3 plus V4 equals the total voltage. If we play around with the algebra a little bit, what we are told, what we get is that the effective capacitance of the series combination can be found by adding the inverses together and then taking the inverse of the sum. Capacitors in series are exactly like resistors in parallel. Add the inverses, take the inverse of the sum. And from the previous slide, capacitors in parallel are like resistors in series. You just add them up. Don't mix those two ideas. Capacitors in series, the math behind it is the same as resistors in parallel. Capacitors in parallel, the math behind it is the same as resistors in series. Be careful, please. Let's find an equivalent resistance for this nasty guy right here. As we move from left to right, we have to go through this 12 nanofarad capacitor, but then we reach a decision point. We can take the path in which we have the 4 nanofarad, 6 nanofarad, and 3 nanofarad together, or we can go through the path in which we have the 8 nanofarad capacitor, followed by a combination in which there's a 2 nanofarad capacitor and a 3 nanofarad capacitor in parallel. The same approach to doing a complicated looking combination of resistors. You have to be able to look at the big picture, break it down into the smaller pieces, determine what's going on in each of the smaller pieces, and then build it back up into the big picture. It's still the same. And one of the small pieces that we have in this particular circuit is the parallel combination of the 2 nanofarad and the 3 nanofarad capacitors. Because they are in parallel and they are capacitors, we just add them together. So this little parallel combination, the 2 and the 3, gives an equivalent capacitance of 5 nanofarads. But now, this equivalent 5 nanofarad capacitor is in series with this 8 nanofarad capacitor. So I have to do 1 over 8 plus 1 over 5 and then take the inverse. And I find that this lower arm of the circuit, the 8 followed by the parallel combination, has a total equivalent capacitance of 3.08 nanofarads. So that's this arm, this lower arm of the circuit. What about the upper arm? The 4 and the 6 and the 3 are in series. So we got to add their inverses, and then we take the inverse of the sum. So the equivalent capacitance of the upper arm is 1.33 nanofarads. This upper arm of the circuit, which is 1.33 nanofarads, and this lower arm of the circuit, which is 3.08 nanofarads, are themselves parallel to each other. So the equivalent capacitance of the upper arm of the circuit and the equivalent capacitance of the lower arm of the circuit, I just add them together, and I get 3.08 plus 1.33 equals 4.41 nanofarads. We're almost done. We still have this 12 nanofarad capacitor to take into account. Remember, we had to pass through the 12 nanofarad capacitor, then somehow pass through this messy combination right here before we get to the other side. Well, this messy combination right here has an equivalent capacitance of 4.41 nanofarads. So the circuit has been simplified to a 12 nanofarad capacitor in series with a 4.41 nanofarad capacitor. So we have to add their inverses together and take the inverse of the sum, and that's 3.23 nanofarads. That's the equivalent capacitance of this entire combination of capacitors. Here's a little bit of a semi-conceptual, a little bit calculation sort of question. Take a look as you move from left to right through this portion of a circuit that involves capacitors. Each of these capacitors is identical. Each of these capacitors is C, has a capacitance of C. What's the total equivalent capacitance of this combination? Again, think about it. Ask me questions if you're not sure. Moving along. Okay, maybe you are dreading this possibility. Let's discuss it. A circuit with a resistor and a capacitor and a battery. All three of these circuit elements in the same circuit. This is called an RC circuit for obvious reasons. It's not called a VRC circuit because any circuit requires a voltage source, so mentioning the V kind of becomes superfluous. But knowing that it's an RC circuit tells you there's a resistor and a capacitor. What happens? Well, it depends a little bit on the initial conditions. Let's imagine that the initial condition is that this capacitor starts off uncharged. And at the instant this circuit is hooked up, I get the current running through the circuit, and of course there's a resistance. So Ohm's law puts a limit on that current. But what happens is this charge starts flowing through the circuit. It starts to build up on the upper plate of the capacitor. And in turn, we induce a current in the lower part. We get a buildup of positively charged plates on the upper capacitor. That's pushing away positive charges built into the conducting material in the lower part of the capacitor, and those positive charges start looping around. We get a buildup of positive charges, and equivalently, we get a buildup of negative charges on the lower plate. But as we start building up positive charges on the upper plate, that's going to start slowing down the current. Because not only now does the current have to fight its way through the resistance, but it's also going to be repelled by the charges that are building up on the upper plate of the capacitor. So the current in the circuit is not going to stay at its maximum value as dictated by Ohm's law for very long. In fact, the value of the current through the circuit starts to decay immediately. The maximum value, according to Ohm's law, would be the maximum voltage divided by the resistance of the circuit. But because of the buildup of charge on the upper plate of the capacitor, that acts to try and suppress the current. The battery keeps trying to push more current through the circuit, but the amount of current that the battery can push through it is decreasing because of the buildup of charge. And it is possible to derive an equation. It actually involves calculus. We're going to ignore that part. To derive an equation for the current as a function of time, it's equal to the maximum voltage divided by the resistance times e to the minus t over RC. RC is in the denominator of the exponent, and the numerator of the exponent is minus t, where t is time. We could also look at a plot of the voltage across the resistor. Just across the resistor, the voltage can be determined from Ohm's law. It's equal to the current times the resistance. The resistance doesn't change, but since the current is dropping off exponentially, that means the voltage drops off exponentially as well. The voltage across just the resistor. On the other hand, the voltage across the capacitor increases, and it approaches this maximum value. You can see the expression, the voltage across the capacitor is equal to the maximum voltage of the circuit times, in parentheses, 1 minus e to the minus t over RC. Why does the voltage across the capacitor kind of look like the mirror image of the current through the circuit and the voltage across the resistor? And that's because we still obey conservation of energy. If I make a closed path around that loop, Kirchhoff's loop rule still applies, and the change in voltage across each is going to have to add up to 0. The battery supplies voltage. I lose some of that voltage as I go through the resistor, and I lose the remaining voltage as I go through the capacitor. The voltage across the resistor plus the voltage across the capacitor must be equal to the voltage supplied by the battery, which is constant. So VR plus VC equals E at all times, no matter what the value of T is. The charge on the capacitor, since it's proportional to the voltage across the capacitor, looks like a curve exactly the same as what you see on the screen. Now, one of the things that you might find maybe a little bit surprising about an RC circuit is that when you take units of resistance and multiply them by units of capacitance, you wind up with units of seconds. That's it. Ohms times farads equals seconds, as surprising as that might sound. And in an RC circuit, the quantity R times C is called the time constant of the circuit. And as it says on the screen, it's a rough indication. It gives you a good order of magnitude for how long it takes for the current to change, or for how long it takes for a decent amount of charge to build up on the capacitor. It just gives you a time frame. Not a hard and fast, we're done after this time, but it gives you an idea for the time scale over which this process happens. The quantity R times C is sometimes called the time constant, and when we talk about a time constant, we often see it represented by a lowercase Greek letter tau. So that's what that script-looking T is. It's a lowercase Greek letter tau. Let's take a look at an example. We have a 72.5 microfarad capacitor that is initially uncharged, and it is hooked up in series to a 573 kilo ohm resistor. This circuit is hooked up to a 9-volt battery, and we want to ask what is the charge on the capacitor 7.65 seconds after we make this connection. We can determine the time constant. It's equal to R times C, so 573,000 ohms. And the capacitance is 72.5 times 10 to the negative 6. And when we multiply this out, we get 41.54 seconds. The amount of charge we can get from Q equals C times the voltage across the capacitor. And if you'll recall, our expression for the voltage across the capacitor is equal to the maximum voltage of the circuit, 9 in this case, times 1 minus e to the minus t over RC. T is 7.65. RC, the time constant, is 41.54. Plug it all in, and you should practice this. You should get 1.10 times 10 to the negative 4 coulombs. And if this had been a test question, and I think it is a reasonable candidate for a test question, you might see the answer written as 110 microcoulombs. Let's have a little fun with another conceptual question. We have one capacitor and one resistor, and it has a time constant of T, capital T. Let's replace that single capacitor with 3 identical capacitors in parallel. And let's replace that single resistor with 2 identical resistors in parallel. What is the new time constant? Is it still T? Is it 3T over 2? Is it 5T? Is it 6T? Again, somewhat conceptual, somewhat quantitative. Play around with it. Let me know if you have questions. It's important to understand how to measure voltage and current if you ever get into this field. I know you won't, but it's still hopefully going to provide a little bit of insight about how circuits work. When you measure current in a circuit, you want your current measuring device to be hooked up into the circuit. You want the current flowing through that device. But you don't want that device to affect the current. What would affect the current? Well, if my current meter had a lot of resistance. If I have a lot of resistance and I hook it in series in the circuit, that changes significantly the overall resistance of the circuit. In turn, that changes the current through the circuit. And we don't want to do that. So a current meter has very small resistance. On the other hand, if we choose to measure the voltage, we basically are sampling the energy at one location and comparing it with a sampling of the energy at another location. And what we want to do is we again want to affect the circuit as little as possible. A voltage meter is hooked up in parallel with the circuit, whereas the current meter, as I said, is in series. The voltage meter is in parallel with the circuit, but I don't want it changing the overall resistance of the circuit, because that will change the current, that will change the voltage, what have you. But by hooking it up in parallel, the best way to have no effect on the circuit is for the resistance of the voltmeter to be huge. Remember, we determine resistances in parallel as adding the inverses. If the resistance of my voltmeter is huge, 1 over huge is extremely small, virtually 0. So that's not going to affect the total resistance of the circuit. So you can look at a circuit diagram in which you are measuring current and you want your ammeter, it's called an ammeter, it measures the amps, so it's called an ammeter. You want it in series and you want it with very tiny resistance. And if you're going to measure voltage, you are going to want it in parallel and you are going to want it to have gigantic resistance. I hope that all makes sense. Take care.